read it to you. Let's say deploy valve here. You have a little bit of oil, and this oil is very thick, viscous thick. It goes through this pipe, and it obviously it makes an overflow here. So what happens? This oil is going to just go down very, very slowly because it's viscous. And if you take a control volume around this area like that, what happens? The pattern you see is very similar. So let me draw it here. So I'm taking a control volume on that, a tiny fraction of that. And the pattern is like this. This is the one. And the flow is going down like this. The thickness is A. And the velocity profile, the velocity here is 0, and the velocity here is some V, right? And the velocity is obviously like this. It goes from some non-zero value on the edge, right? And then it goes to 0 at this point. So that's what we have here. Now, one thing you can say, before even you solve this problem, we got to find the boundary conditions. It's very important. So one boundary condition here, the velocity, or what is u, right, at wall is what? 0. This one boundary condition. What about this point right here? Is the velocity 0? So what is 0 there? Do I have a boundary condition there? You see, look, if this is your, let's say this is your y, and this is your x. Coordinate system. Right? So you kind of, here's my conventional.
Would the y be 0 there? Or
yeah, if this is my conventional xy, I just rotate it 90 degrees. You see that? So that's your x and that's your y. Now, look at here. Let me rotate this back into my conventional xy. So this is kind of rotated 90 degrees this way. So this is your x, this is y, and the velocity profile you see is like this. And this is your u of y. Do you see that? So I know that u at y0 is what? 0. But what about this point, this is your point A, at y is equal to A. This is the thickness of my oil. What do I see here? The derivative of u with respect to y is 0, right? Look at this slope, the tangential. You see the derivative of u with respect to y is not 0 here. It's not 0 here. Do you see that? But when you reach to that, you get a flat line. The derivative of u with respect to y is 0. So what is that? This is just, you agree that this is shear towards u dy 0. So that means the shear here is 0. Obviously, why the shear here is 0? Because the friction between the oil and the air is very small. You see these two fluids, the air and the oil, are actually in contact, but that force is just so tiny that this derivative is 0. So two boundary conditions. One, velocity here is 0 at the wall. The other one, du dy is 0 at y is equal to a. This is y is equal to a, the derivative is 0. So two boundary conditions. You see that? Now, question here is, it says, find the velocity profile. Now, what it says, give me the exact relation for that. So how can I solve this problem? One way we did in chapter 2 is to assume this is parabolic second order. So you assume, you have done it in the homework unless you cheated and used the solution manual for the homework. But if you have done it yourself, you already know what I'm talking about. So you say u is equal to a second order function of y squared plus py plus c, and these three are unknowns. And then you apply the boundary conditions to find these three. That's one way, right? But what's the other way? You see, we assume that this is second order. We assume that this is second order. Plug it into the boundary condition, get ABC. But is this a real assumption, physical assumption? I don't know. The only way through it is to solve Navier-Stokes equation. If I solve Navier-Stokes equation and I get something, that is definitely the physical thing. That is the real world. That is not an assumption. So let me write down the Navier-Stokes equation and then go through each term, simplify it, apply boundary conditions, solve it, and then see what I get for lossy profile. So here, these are the Navier-Stokes equations. So in the final exam, I give this equation to you in the appendix. You don't need to memorize it. And then all you need to do is to go through these steps and see what term is what. Is this term zero? Is it non-zero? If it's zero, put it zero. If it's non-zero, just leave it and then solve it later. All right? So the first equation is this. Partial d plus u x plus rho b y plus d rho w u. What equation is that?
The differential form of the continuity equation?
Exactly. I know a lot of you guys know that, but guys, if you don't know this, this is a very bad indication. When I was grading the quizzes, I saw a lot of people did it right. The last quiz was basically just, what's the name of the equation? You see what I'm saying? And I saw a lot of people, well, obviously that's what I expect, but some people, they even didn't know what the name of the equation was. So what does it mean? That means I have spent this much time to get this equation and understand, because you really need to understand how these equations are obtained in order to be able to use it. And that means the entire thing is wasted. Although we have videos, but I go to the videos, the number of views is just 10 out of 32. We have 32 students. They don't watch the videos. You see, if this was a trade school, right? What do they do in trade school? They just give you the charts and say memorize. You do that. If they ask you to do this, use this table, use this chart. That's a trade school. This is not a trade school. This is engineering school. That means you have to know exactly what term is what. All right? And if you don't know it, you're not an engineer. You're a technician. You're not an engineer. And sometimes you have, in the fluid mechanics, you have 40% of class fails, F. I mean, I can't up it to like C or pass. I can't. Because you already have a lot of A's. I can't care the grades. But look, the only way through that is to get waivers. We still have opportunity to get waivers. The only legal way to get through it is to use waivers. But that was in the syllabus. That's the only opportunity you can contribute. So this continuity equation, x momentum, this one rho u t plus rho b. Y momentum the zero on top. There you go. And also we have energy equation. But look, energy equation, we only are interested in energy equation if we have the huge difference in the temperature or huge amount of turbine work or things like that. We have energy, we have to solve energy. But here, when we assume that everywhere temperature is ambient temperature, the pressure is exposed to the atmosphere, so the pressure is same everywhere. So in this problem, the energy equation is not something that you're interested to solve. You could, but it's just waste of time. Now, let's go over each term. Before I go over each term, I want to show you that control volume. This is the coordinate system I take. I already showed it to you. So for the fluid, going this way, this is the wall. This flow is back here. The thickness is A. And if I zoom over this control volume here, I have this is the wall. And the velocity is back here. And it's same. So you get the same pattern going down. Velocity here is 0, u at y. See now, this is my y. This is not x, this is my y. That's all it is. At y 0, here is what? Here at y 0 is what? 0. And then, because the thickness, that's my layer. That's my layer. See? That's the fluid, the oil. That's the oil. And A, this is from here to here is what? A. U at y is equal to A is equal to du dy at y is equal to A is equal to 0. So there's two boundary conditions. Now before I apply boundary condition, I need to simplify that. Because in general case, this is a huge amount of differential equation and it's impossible to solve. So what should I do? I'll go over every single term and see what I get. First of all, is this transient? We pay attention to the question and say the oil is very, very viscous. That means this motion is very, very gradual. You don't even see it. You have to wait 20 minutes so you see it going down. All right? So what can I say? And if, in particular, if I take the control volume around here, I don't care if it's going down because the flow comes the same pattern and leaves the same pattern around here. You see that? So in that case, is that a steady state?
Yes.
For that control volume? So what should I do if it's steady? That's what we do in the final exam. I'll give you this equation and you have to tell me the reasoning why these terms are 0. All right? So this is steady state. All these transient terms are 0. Right? And what else? What else is obvious? Look, the velocity is only in the x direction, right? So what about my v? You see, these are the components of velocity. V is equal to u, v, w, right? Again, the very first two chapters, we have kinematics of fluids. We have the velocity and we integrate it to get a streamline. You remember that? All right. So here, which one is non-zero?
U.
Only thing is u is non-zero. This is 0. This is 0. Why? That is in the final exam. You need to show me why you are not zero. You need to draw that in this direction. I don't have direction. This is V, right? No component in this direction, and no component. This is your W. No component in this direction. So when my V and W is zero, what do I get in the equations? Let's go over every single thing. First of all, W is zero, so that means every derivative of W is zero. You see that? Now, where is the direction of my gravity force?
In the X.
Let me ask. The random number. Maybe I should have. The direction of gravity force is this way, right? What direction is that? Positive. Right? So, what do I get for GZ, gravity in the Z direction? Zero. What about GY? Alright? So, what about these terms? The second derivative of W? All zero, because all of them are zero. Right? That's very interesting. So this equation is like everything is zero except the pressure gradient. So look, Navier-Stokes equation tells you the pressure gradient must be R to zero in order to this equation is satisfied. So let's see what's the physical meaning of that. It says the difference in pressure in this direction is zero. Is that right? Well, the pressure everywhere is same. Why? Can you tell me? The pressure of this fluid everywhere is same. Why?
It also has an atmosphere suggested.
Say that?
Open to atmosphere.
Open to the atmosphere. The pressure in X is same in Y. So the gradient in all directions same, which actually satisfies also Navier-Stokes. It must be, the pressure gradient must be zero because every other term is zero. You see that? So this also is zero. So look, the last equation is not useful at all. Do you see that? But I'll just give you for the purpose of final exam, just to show me, and you have to write this easily. I may make it a multiple choice question. Right? So there are a lot of different ways I can put the assessment, how you can understand it. Now let's go to this equation. What do I get for that? Zero. Why?
No velocity in Y.
No V, right? It's everything is U in X. What about this step? Zero. Both V and derivative is zero. So 0 times 0 times 0. This one? Zero. W is zero. So this one, U is not zero, but because V is zero, the product is zero. What about the pressure?
Zero.
So when I say Y, I'm talking about this direction. We usually think that Y is this direction, right? Make sure you talk about that direction. So zero, and you see that even if you say, well, I don't know about that, you know that this is zero, this is zero, this is zero, then this must be zero. We satisfy the condition that they said that this is exposed to the atmosphere, so pressure gradient is zero. Why? Pressure is zero. It's exposed to atmosphere. It's not inside the pipe. So this is the equation I get. And then the first equation, is this zero? Is this zero?
No.
So I don't really know about that. It's kind of like suspicious. So I just leave it like that. But some of them are obviously zero. For example, this one. Zero times whatever it is. This may be non-zero. But this 0 times non-zero, 0. What about this? 0 times non-zero, 0. Also, this is also 0. There is no change in the Z direction, right? What about gradient of pressure in the X? Do I have pressure gradient in the X? Well, again, the pressure is same. That is, in the X is not changing. What about GX? Is it zero? It's not zero. You see, there is a G in the X, and it's positive. So leave it like that. So this term is also suspicious. I don't know about that. This term is suspicious. But those guys are zero. What about this term? I don't know about that, right? Because I know that I have a U, right? I know I have a U is this, but I don't know about the secondary. So just leave it like that. What about this term? Well, look at it. in the y, u is changing. So the second derivative is also changing. So I don't know about that. Leave it like that, it's suspicious. But what about this term? Does it, in the z direction, in this direction, does it change? No, it doesn't change. So this is 0. No change in the z. So these are the terms that are possibly non-zero. Let's see. Come here. Take the row out. So you put row out. Why I put row out?
It's constant.
This is one of the, because it's incompressible, constant, right? Take it out. Take it out. This is v. It's 0, right?
Yes.
So this is 0. What about this guy?
0.
So what do I get? Rho times from this equation. If you solve it, let me use a different color. If you solve that, you get what? This equation gives you rho. The gradient velocity is what? What can I say? What can I say about this? This is 0 because rho is non-zero, right? So the only way through it is gradient velocity is 0. So this is the first finding, useful one. Now look at this term. What is it? U times the gradient velocity. U was not 0, right? But according to continuity, the gradient velocity is 0. So what does it mean?
It's 0.
Now you may say, well, you know what? I'm a little bit scared. Everything is becoming 0. That means I can't solve the problem if you have every 0, right? Well, look, just wait. This is 0, right? What else? Look at this term. What is that? The derivative of
The gradient.
velocity, gradient velocity. So this was already according to continuity 0. So the derivative of that is what? 0. So the final equation that is not 0, I want to write it here. So the only term, these are all 0, right? Is what? 0 is equal to, this is non-zero, rho g. And what's the gravity in the x? Just g, right? 9.81. Plus mu times, you see, the only non-zero one. This is the one that you cannot make any assessment. You cannot say it's 0. This is, you could. You get it from continuity, right? This one, we have no idea, so you just leave it like that. So that's your x momentum simplified. So this is what I want from you in the final exam, simplified x momentum. So here everything is 0 except rho g and this term. Mu times the derivative of mu with respect to y. Now, simplified y momentum is what? This guy must be 0. This is simplified z. Let's put it here, simplified z. Simplified z momentum. It gives you the p in the z is 0. Which is makes sense according to the physical interpretation. Simplified y momentum is what? Gradient in respect to y, 0. And this is x momentum, and continuity is simply that. This is simplified continuity. Simplified continuity. There you go. Now I want to solve these equations. Well, look. If I solve this equation, what do I get? Let's solve this equation. This says that u derivative, let's solve this. U with respect to x is 0. What does it mean? That means if you integrate that, it says u is equal to a function of y, u of y. Right? Why? Take a derivative of that, it's only a function of y. Take a derivative with respect to x, what do you get? Say that?
Only function of x.
No. It says u with respect to x is 0. When you integrate that, what do you get? U only is a function of y. Why? Because when you take the derivative with respect to x, you get 0. right? So if u is a function of y, then I can solve this simple differential equation. So let me solve that. This goes up. So this equation, I want to solve it. So I have take rho g to the left, negative rho g is equal to mu. Now you have d u dy squared. Why? Because u is only a function of y. It's just regular second derivative. It's not partial derivative because u is only a function of y. Now divide this by mu and integrate. First integral, you have what? Negative rho over mu g y plus c1 is equal to du dy. Right? So this is just a constant, negative rho g over mu times y plus c1 is equal to du dy. Now what's the boundary condition? I have the first boundary condition here was du dy and y is equal to a must be 0. That was one of the boundary conditions. Let's apply. Put y is equal to a. So that's what I do. Negative rho over mu g. Put y is equal to a plus c1. This must be equal to 0. So c1 is what? C1 is equal to rho g over mu a. Alright? Now, go ahead and do one more integral of this. One more integral, both sides. So you get what? You get negative rho mu g y squared over 2 plus c1 was what? Substitute value rho g over mu a. This was c1 already times y plus c2 is equal to u of y. Now, I'll apply the second boundary condition. The second boundary condition is say u at y is equal to 0. Here, okay? U at y is equal to 0 is what? 0. So put y 0. This is 0. This is 0, right? If you put y 0, so you get c2 must be equal to u at y 0, which is 0. So that means c2 is 0. So the final uy is what? The final relation for uy, u of y, is equal to negative rho over mu g y squared over 2 plus rho g mu a y. So let me write it down here. You have u of y is equal to negative rho g mu times y squared over 2 plus rho g mu times a y. So that's what we got. And going back to the slides. First, let's see if the boundary condition is valid. If you put y is equal to 0, what do you get for u? 0. Take a derivative of that. The derivative of u is what? Is equal to negative rho g over mu times y plus rho g over mu times a. Right? That's the derivative of what? Put y is equal to a. The derivative must be 0. Is that right? Right, so that's the solution. Now let's go back to the slides. see, compare our results. Yeah, this is what it is. Well, I forgot to put the result from the book, but it must be this. Do you have the book? Can you check? Let me simplify that. You can factor out this term. So you can write it u of y is equal to rho g over mu times ay minus y squared over 2. All right, it must be this. Do you have the book? Anybody has a book?
That's 712.
Yeah, that's 7. Seven 12. It's page number 412.
I must have a different book. Second edition.
Yeah, it's let's see. Differential. Right. All right, next problem.
Professor,
Yeah.
I have a question. On that, cylinder, why, if all around it, in this direction is the same, why do we get different points going lower than others?
Okay. That's a good question. The reason that we get a different point going, you see, this is a very interesting question. It says that you have a cylinder, right? In the real life, if you put a pump here, this water comes here, or whatever oil it is, it's not gonna go like this, right? It's not gonna go uniformly down. Some places it goes like this, some places it goes like that. Do you see that? It goes non-uniformly. Some places go faster, some places go slower. Can you tell me why?
Imperfections in the polishing of the material.
That's right. So look, this initially, when you add a pump here, first of all, you don't have a uniform pipe all around it with the exact same pressure. The pump is here. So that means the pressure here is most likely higher than here. So these go faster initially. Everything depends on initial condition. Look at the Navier-Stokes equation. You see you have an initial condition. And you have to integrate. That's a transient problem. This one, that you have time-dependent study of the edge, that's a transient. When you integrate, what's the initial condition? Do you remember that? In the differential equation. How many of you guys had differential equations? A lot of you had differential equations.
Is it the plus C?
Huh?
Is it the plus C? Your initial conditions?
Is the what?
Is it the plus C when you integrate?
It's the initial condition. You remember that initial condition? Yeah, this initial condition. So depending on the initial condition, which is imperfection of manufacturing or different pump location, you get different initial condition. If you get different initial condition, you get different displacement. So that's because of that. But in the hypothetical approach vision, if you make everything symmetric, everything perfectly made to the 16 significant digits, when you run that experiment, it takes $2 billion to make that. But you see that everything is Beautiful.
Okay,
Okay.
thank you.
Mhm. Next problem, we go to, now we want to do dimensional analysis. Now this is a good chapter, just like energy equation. It makes your life a little bit easy. As you can see, the title says, finding a relation between physical parameters without solving Navier-Stokes. So one way is, if you are a very good mathematician, you just solve all these equations. You're just ruthless, right? I solve everything and I get it. But one way is you say, this is just so hard. In fact, when the geometry is hard, this problem becomes almost impossible to do. You have to use a software to do that. But look, there is always something called dimensional analysis. And dimensional analysis is a way to find the relation without solving Navier-Stokes. And how you do that? Well, I just want to give you something. Do you remember when we had a basic equation, F is equal to ma? They said in the physics course, they said the dimension, the physical dimension of both sides of the equation must be same. You remember that? They said if you want to spot an error in a new paper, like somebody finds a new relation in physics, and the first thing they do, they try to see if the dimension of both sides of the equation is same. If it's not, they reject it. So for example, if for this equation, somebody gives me, say, I got an equation, F is equal to ma, m times derivative of v with respect to t, or a. Then the question is this equation valid? We don't know, unless you go through the derivation, right? But look, the first thing to see if it's valid or not is to say, well, the dimension, this bracket is a notation for dimension, right? The dimension of both sides must be same, right? So what's the dimension of F? Is if you go to the table of dimension, this is equal to m L t minus 2. So how do you get that? I'll talk about it soon, right? So that's for m, and then for mass is what? M times, you get the t here at the bottom, and velocity itself is L over t. So you get what? M L t minus 2. So they match. And if it's not matching, that means this equation is wrong. But if the dimension matches, you need further derivation to show that the equation is right. Otherwise, it may be physically non-valid. But this is, I would say, this is a necessary condition for the equation to be valid. Now, we use this in a more elaborate way. They call Buckingham theorem to find different parameters governing the equation of fluids in a complicated problem. And before I talk about it, I want to go over these tables and see how these terms are obtained. For example, you see area is what? The first one, area, it's just length times, let's say you have a general area, right? You just make it circle, different example. So it's pi r squared, right? So what's the dimension of area? Pi does not dimension, the dimension of r squared. So what's the dimension of r squared? L times M, or L squared. So instead of meter or feet, they say L. L means length, right? Length. So length is squared. What about volume? Well, volume is always area times the height, right? Area was what? L squared times another L, L cubed. This might be a fun little example, just say, find the dimensions of pressure. One quick question, right? And so on. You go to velocity. Velocity is what? Meter per second or feet per second, whatever, right? And say meter per second. What's the dimension of meter? L. over t. They don't say second, they say t, that means time. So you bring the t up, you get ft minus 1. For acceleration is what? Velocity per second, right? So velocity was what? Mt minus 1 per second. You get L, t minus 2. So that's what you get. And so on. And you see, for example, they say force. What's the dimension of, how do you find the dimension of the density before we do force? Density is what? You go to the definition. Density is mass per volume, right? So take the dimension of density is that, which is in bracket M over bracket V. The dimension of mass is what? They call it M. So far what we had, what? M, L, T. Right? Now, if you have temperature, they use theta. Some people use K or theta. That's for temperature. But MLT is usually the most, you see every time you have MLT. One for length, one for time, one for mass. Alright? So here density is M divided by what was volume? By Q. So you have M L is 3. Right here. And I want to do the force. What's the dimension of force? We already got it. Did I get it? Yeah, ML T minus 2. There you go. And then you have, if I get find the dimension of pressure. How do you find it? Well, pressure is what? Use the definition, force over area. So you have to find the dimension of that, right? So what is that? It's bracket F over bracket A. What's the bracket F?
MLT.
Right here. You can get it from table. M LT minus 2 over bracket A. L squared. This cancels out with this. You get 1L, so you get M L negative 1 T negative 2. Do I have pressure here? Okay. And so on. I'm going to give one of these and say find it. Very, very easy question. Now, before I show you the Buckingham pi theorem, I want to show you some important dimensionless number. I know that some of you guys already know the Mach number. Right? Have you heard Mach number? Mach number. When they talk about missiles like supersonic
Mach number.
or Mach number. Some people say Mach, some people say Mach, some people say Mach. So I don't know which one you want to use, but that is just a parameter. That is nothing like a negative. It's not a region. It's not a constant. It's just a parameter, and it's defined. M is defined as a Mach number. It's defined U over C. And what is U? The local speed of fluid divided by the speed of sound at that point. So if you have a flow here, right? So the velocity here, say the magnitude of velocity is U. The magnitude of velocity divided by the speed of sound there. What's the speed of sound there? Usually the speed of sound is 341 meters per second. Right? But depending on temperature and the property of the fluid, the speed of sound may change. Right? So if you do that, then you realize most of the time we do in this course, Mach number is very smaller than 1. Why? Because the speed of fluid is very smaller than the speed of sound. It's very smaller than 341 meters per second. Let's say the speed of fluid is what we had in the wind tunnel. What was it? The one we had in the wind tunnel? Let's say
55 miles an hour.
yeah, let's say it was like, let's say 10 meters per second. For example, that's the speed of fluid. It was like 341 meters per second. That's the speed of SAM, that's the speed of fluid. What do you get for Mach number? Very small value. Very small value, you see that? Always zero. So when you go supersonic, this value is greater than 1, obviously. You see supersonic, because this is sonic. This is the speed of sound. Supersonic, you go, it's just a number, you see? There you go. Another important parameter is Reynolds number. Again, these are dimensionless parameters. That means we don't have a dimension for that. If you take dimension on both sides, take a dimension on both sides. Let me do that. Take dimension of Reynolds number. Reynolds is rho VL over V, right? I take the dimension, bracket. So what do you get? You get bracket rho, bracket V, bracket L, bracket M. So for rho, you can just use the table. I mean, you can derive everything from scratch, or if I give the appendix like this, use that. What should I put for rho? M negative 3 times volume is what? 3 times L divided by the viscosity, the dynamic viscosity, which is M L minus 1 T minus 1. M L minus 1 T minus 1. M cancel out with L. You get oh, I'm sorry, for V, this, I thought this was volume, this is velocity. So you get L T minus 1, right? For this velocity, where is the velocity? Velocity is here, right? So you get L T minus 1. So L, ML negative 3 times L T minus 1 times L divided by kinematic viscosity, which is dynamic viscosity, which is M L minus 1 T minus 1. Now, see, this cancel out with this. This is with this L squared with L negative 3, you get L negative 1, cancel out with this. This one cancel out with this, and M cancel out with M. So you get what? 1. If the dimension is 1, what does it mean? It's dimensionless. There is no T or L remaining. Right? There is no dimension. So all of these parameters you see are dimensionless. There is no dimension. So the other one is Euler number. They never use this Euler number. And the other one, the Freud number, they use this in civil engineering when you have hydraulic jump. But it's not frequent in mechanical engineering. But still, these are just a bunch of dimensions. Now, the Buckingham Pi theorem says that if you have n number of physical quantities, so let's say I have one problem that let's say you have a beam this is a ring of aircraft, and we want to find the amount of lift generated by this ring. Alright? And this is the flow. And one way, again, is to solve the Navier-Stokes equation, which you can use to numerically solve it. That's one way. Another way is to say, well, you know what, I know this lift will depend on, so lift, these are the parameters involved. These are the parameters involved in this problem. One is lift, right? The other one is what? I know the lift will increase if the flow is viscous, right? Or decrease. So one is viscosity. How do you know that? Well, in fact, viscosity is very small, the effect of viscosity on the It's very, very small. It's more on the drag. But the way you know that, you just go to the lab and put this in the wind tunnel and test it. And you put a more dense fluid, and you see the lift increases, right? So another parameter is what? Rho. Another parameter on the lift is what? The free stream velocity. Do you remember the wind tunnel increased the velocity, and then the drag increased? You remember that? So all these parameters also depend on velocity, and also it also depends on the surface. Like the bigger surface of wing is, the higher lift and drag it gives you, right? Both of them. So what you do, you see, look at this. This is a list of physical parameters. Now the Buckingham pi theorem is saying if you have n number of, so number of this, we call it n. You have n number of physical parameters and n number of LTM basic dimensions. You see LT things that we have in this table, they call it basic dimensions. These are basic dimensions. So the Buckingham pi theorem says that if you have n number of physical quantity and n number of basic dimensions, then n minus m is the number of dimensional less parameters involved. Parameters involved. They call this high parameter. Now look, for example, let's say if I have 5 physical parameters, and if I have basic LTM, these are my fundamental dimensions. So n in this case, n is what? 5. N is what? 3. So 5 minus 3, 2. I have 2 dimensionless parameters. How do you find it? You just do the same thing. You see, you remember we did a physical DNA? Take the dimensions and then make sure that the dimension matches. You do the same procedure, which I'm going to do this next class, and then you can find all the dimensionless parameters. It's very easy. Once you do it once, and then you say, well, I hope he gives something like this in the final exam. Because the procedure is very routine and you can memorize it. All right?